give you bounds and probabilities when, if we don't know anything about the probability distribution, other than maybe the mean or the mean and variance, the Chebyshev inequality and Markov inequality can give you bounds on certain probabilities. So you can still say something about the probabilities, but not too much. Here's position, Markov inequality. If x is a random variable taking only non-negative values, then for any a greater than 0, the probability that x is greater than or equal to a is bounded above by the expected value of x. So if all we know is that x does not take negative values and we know the mean value of x, we can bound this probability this way. We can get an upper bound. Let's do the proof. It's really simple. So define another variable y that is equal to that indicates indicator function, which this new random variable takes the value 1 if x is greater than or equal to this constant a and is 0 otherwise. Then let's first convince you that this is true. This random variable I is always going to be less than or equal to x over a. Because this random variable either takes the value 0 when x is less than a. X is non-negative, so x over a is always greater than or equal to 0. If I takes the value 1, it means x is greater than or equal to a. If x is greater than or equal to a, so I equals 1 if x, that is x over a is greater than or equal to 1. So when I is 1, x over a is greater than or equal to 1. So you always get this inequality. This random variable will always be less than this random variable. Okay. So what do we know about properties of random variables? If one random variable is always less than or equal to the other, the expectation of this is one of the properties of random variables that I mentioned, I think, 2 weeks ago. So this is always true. This is just 1 over a. I can pull the constant out, expected value of x. What is the expected value of I? So I takes the value of 1 with the probability that this happens. 0 probability x less than. So this is just probability x greater than or equal to. And with this way down. They're both using that. Here, we get probability x greater than or equal to a is bounded by expected value of x over this kind of argument, if you get into mathematics or anything where you have to do simple proofs, this is a very useful argument. You can, if you construct an indicator function like this, then you can always bound it by x over a. All right. So even when you know nothing much about your random variable other than its mean, you can say something about its probabilities, that is bounded above by. Now, this bound may not give you that much information. Say, if expected value of x is 2 and your a was 1, then you get this probability is bounded above by 2. It doesn't give you much information because you know probability is anyway bounded by 1. Okay? So this bound may not be useful, but sometimes it can be useful. Now, the next one is Chebyshev's inequality. And what that says is the following. And x be with mean, that is the expected value of x mu, that is, this is the expected value of x, and variance sigma square. But x doesn't have to be non-negative. Then the probability that the distance from x from its mean, the probability that is greater than or equal to c, is less than or equal to the variance of x over c squared. And like the Markov inequality, this bound that you get may not give you a lot of information, especially if this bound is greater than 1. It definitely doesn't give you any information. But these two inequalities, Markov's inequality and Chebyshev's inequality, they come in very handy when you want to bound things when you do proofs. And in fact, we will use this Chebyshev's inequality to prove what's called the weak law of large numbers. So there are two very important theorems in probability. One is the central limit theorem, the other is the law of large numbers. And you need the Chebyshev's inequality to prove the law of large numbers. Alright, so all this is saying is the probability that the deviation of x from its mean, the probability that is greater than or equal to c, is bounded above by this one. Some different ways we can rewrite this. The proof of this is very obvious. X may not be non-negative, but x minus mu, this is. So let's look at this. Now, we could bound this above by expected value of absolute value of x minus mu over c. That's just a Markov inequality. But we don't know what the expected value of this is. But this equals the probability of the same thing squared. So if I know that this absolute value is greater than or equal to c, then the square is always greater than or equal to c squared. Right? So these probabilities are the same, because these are two equivalent statements. And now I can use x minus mu squared is non-negative random variable. I can use my Markov inequality, and what does the Markov inequality say? I can bound the expected value of this random variable. I can bound it above by this, divided by this. This is by Markov inequality. And this is just the variance, so that's sigma squared. Expected value, this is the definition of variance, right? So we're done with the proof. So the proof of these two things is very easy.